Okay, section 15.5. So the last two sections of our class are some geometry sections out of chapter 15. We don't cover all of chapter 15. You will see more of this if you take a geometry course, but we're just touching on some fundamentals that need to be covered. In 15.5, it's volumes and surface areas. So we have two things to do in this section. It's relatively short. We're going to look at some classical volumes of three-dimensional figures. 3D figures. And secondly, we're going to look at some surface areas of some of the same 3D figures, some of them different. Three-dimensional figures. All right, so let's start with some volumes. So we're just going to look at, we have 3, 4, 5, 6 volumes of, or we have volumes of 6 different figures that are classical figures. So we're going to start with the rectangular solid. So the rectangular solid, this volume is V equals length times width times height. And we build those from a rectangular solid that looks something like this. And this would come down. So our length is the length out in front. Our width is the width going backwards, and the height, of course, goes up. LWH. Sometimes you also see this as no, I think it's always length times width times height. Sometimes we call the width the depth, depending on if you're in a structural engineering or engineering perspective, they may call this depth. But that's our volume formula for a figure that looks something like this. Now, of course, this translates into the special volume for the cube, which is just, usually we call it side cubed. And the cube is called the cube because of the mathematical cube. Let's see how well I can draw cubes here. And this would come down, and this would go over, this would go over. All right, so not a perfect cube, but we can pretend. And it's the volume is side cube because it's a cube, so the length, the width, and the height all have the same length, s. It's a perfect cube. Hence the term. 3 lengths, all the same distance. So these are very, very closely related because it's the same formula. The cube is just a special version of the rectangular solid. The next one is a not so common one. It is the pyramid. So the pyramid's volume is equal to 1/3 capital B times H. So little b is usually the base. Capital B is the area of the base. So the reason it's capital B is because there are two types of pyramids that we're going to focus on. We have triangular pyramids and we have rectangular pyramids. Now, as it turns out, every pyramid has this volume, so we're going to talk about different kinds of pyramids in a second here. But a triangular pyramid has a base that's a triangle, and this would be the back. This side goes up, this side goes down. That's a terrible drawing. Let me try that again to make it a little bit better. Let's do it like this. This will look better. So if this is our base, yeah, that's much better. So this is the base, and what we see is the front face. So there are 3 faces to this pyramid. This face here, and this face here. And so our volume says take the area of the base triangle here, which is 1/2 base times height, or 1/2 this distance times the height, and then multiply that by the height of the pyramid. Now the height of the pyramid goes from here all the way to the center of the triangle, or in other words, it's this distance here. So from this all the way to this is the height. It's from the base of the pyramid up to the top apex point. Now for rectangular pyramids, they look somewhat similar, like this, with a rectangle, and then they all come up to a point at the top here. Let's make this a little bit taller. I may have to redraw this one as well. Pyramids are hard to draw for me. That's not the worst. All right. Hopefully you get the idea. This is the base. Again, the height is from the top point all the way down to the center to the floor. So this is our height here. And you take the area of this rectangle, length times width, and multiply by the height, and then multiply it by the 1/3. The idea is each of these gets carved out of a prism or a solid. This would be a triangular prism or triangular solid. This would be a rectangular solid if you filled it in. If you brought these up and made a box out of this thing. So this is our two types of pyramids. Now you can construct a pyramid with a base that has any geometric shape. So square, triangle, circle is special, it's called a cone, which we'll talk about in a second. Anything with sides, I guess, is a better description. So pentagon, hexagon, octagon. This is the most common pyramid. This is the style that when you think of the pyramids of Egypt, they are rectangular in base. That's how they were constructed because it's the easiest. Triangular bases and other shapes, you have to get very specific angles. This one, these are all 90 degrees, even if they don't look like it in my weird forced perspective here. So let's move on to our last 3 volumes. So the next one is a cylinder. And a cylinder's volume is sometimes just base times height. Again, capital B is the area of the base. It's a cylinder, so this is always going to be pi r squared, the area of a circle, times the height. And so our cylinder, it's got a circular base, goes straight up, and then the circle is copied as best you can. And our radius is this distance here, that's r, and our height is the height of the cylinder. So basically you take your area of this circle, pi r squared, and then multiply that by the height. Very similar to a pyramid, but more similar to the solid that we saw, the rectangular solid. So the next one is the cone. So the cone is kind of a mix between a cylinder and a pyramid. So its volume is equal to 1/3 base times height. So this is the same volume as the pyramid, but a cone has a circular base, but still comes up to a point. You all know a cone. Ice cream cones, triangular cups, anything you want to talk about. This is the height. This is the radius. And so our base of our area is the base of a circle again. And so this becomes 1/3 pi r squared times h. So you can see how it's almost a cylinder. If this was to continue up, let me do that in a different color. So if we were to finish this circle like this, we would have a cylinder. The cone is a hollowed out part of the cylinder, and it's exactly 1/3. Similar to how the pyramid is a hollowed out version of the rectangular solid. The length times width times the height, and then it's 1/3 of that. The cone works in a very similar way. So our last three-dimensional figure is the sphere, and the volume of the sphere is probably the one that you know the most. It's 4/3 pi r cubed. And spheres are great, and by great I mean not great because I can't draw them very well. So the best way I can show you how to draw a sphere is draw a circle as if you were going to draw a cylinder, and then instead of bringing it to a point, round it over like this. And then try and copy that on the bottom as best you can. And it gives the illusion of a sphere. Again, I'm not great at drawing three-dimensional figures. I don't expect you to be great either. If you are, that's good for you. So that's our radius. This is really an extension of the area of a circle. We can see that the area of the circle, pi r squared, is hiding in there. So this is 4/3 r times pi r squared. Now the 4/3 r, it just turns out, is a relationship that I want to say it was Archimedes found out. He did a lot with spheres and circles back in ancient Greece. It's not important to know why it's 4/3. You can remember this formula. So we have 6 volume formulas. I just drew over my sphere. The sphere is 4/3 pi r cubed. The cone is 1/3 base times height, or 1/3 pi r squared h. The cylinder is base times height, or pi r squared h. Can't see that I just boxed that in. Our pyramid is 1/3 base times height, b and base being the area of the base, not the length of the base. And then the cube and this rectangular solid are length times width times height, which reduces to s cubed for cubes. So there's not a lot to do. You just kind of have to use these formulas. It's not going to be something of restate the formula in your homework. You're going to be given questions that you have to either in word problem form, or just it's going to tell you to calculate the volume of the sphere that has these numbers. So there's not a lot to do in this section except go over the volume formulas. If you have questions about what the H is, what the R is, those are things that I can help you with in office hours. But there's not too much more that you need to know for volumes except the formulas. That's the hardest part of those questions, is knowing what formula to use. So now we want to talk about surface areas. So we don't do a lot with surface areas. We reduce the number of figures that we even look at. So for a cube is the first one. The surface area, denoted S sub A, or sometimes A sub S, or sometimes just SA. All of these things refer to surface area, depending on who is giving you the formulas. And this is 6S squared. And if you draw yourself a little cube, we can take a look at where this area formula comes from. So the surface area takes all the areas of each surface in your figure. So if this is S, S, and S, we take the area of this face. Now for a cube, every face has the same area because every dimension is S. So it's the front face area plus the top plus the back plus the left plus the right plus the bottom. And there's 6 faces in total, which gives us 6S squared. So if we take this and think about a rectangular solid now, slightly different because rectangular solids, we don't have the same sides. So for a rectangular solid, we'll actually construct the volume formula together here. So I'm going to draw myself a little rectangular solid. Try and make it as much not like a cube. Again, it doesn't need to be perfect. That was real bad. Real not good. So, if we're finding the area of our faces, our first area is height times length, or length times height. It doesn't matter what order you do. So that's this front face. Now there are two faces that look like that. There's this face here. Let's outline it in black. That we just did, the front one, length times height. And then there's another one back here that again is going to be length times height. So there are two, the front and the back. Because this is L and this is still H here. So we have two of those. Then we have height times width, or width times height on the side here. But we don't just have one of those, we have two, because we have this one over here, because this is still W down there. So there's two of these, and you've probably guessed where this is going. The last one is length times width, the bottom, and there's both the bottom here and the top here, so there are two length times widths. And that's our volume formula. Now this collapses back to the cube version. Remember, the cube is special. It has all the same length sides, whereas the rectangular solid has different length sides. And so it collapses. This collapses into the formula for the cube. And the last solid that we calculate surface areas for is the cylinder. Again, it could be, oh, I did volume. Ooh, bad me. This is surface area, or area surface, or SA. My goodness. So surface area, or area sub S, or SA for surface area of our cylinder. The cylinder is a little bit special because it's got the circle. Give our dimensions here, radius and height. So if you were to slice the cylinder with scissors at one of its edges, you could roll it out into a rectangle. Now the rectangle has very specific dimensions. Its height is still its height because we sliced it and unrolled it. And then the length around the circle, which would become the length, is 2 pi r, which is the circumference. So when you are trying to figure out the surface area, you need the area of the cylinder body, right? Like imagine a water bottle in your hand. You need the area of the actual place that your hand would go on that water bottle, which is this, 2 pi r times h. And then plus its surface area. There are two other surfaces. There's the circle up here and the circle down here. Now the area of the circle we know is pi r squared, and there are two of them. So this is where our formula comes from. Now sometimes this is, you factor out the 2 pi r and they leave r plus h here as a different version, so it feels more like a rectangular solid does, but not quite. It doesn't matter if you memorize this version. This is all you need to know. But that is our third surface area formula. And if you think of this notion of what surface area represents, surface area, as I've been saying, is the area of all surfaces of a three-dimensional figure added up. So you can take this to the sphere, not the sphere. You can take this to the pyramids, for example. And we could get the area of the base, the area of this triangle, the area of this triangle, and the area of the front triangle, add them all up and get our surface area, and you could make a formula. These are the most common 3 figures that we calculate surface areas for. They're not the only ones. There is a surface area formula for the sphere. There's a surface area formula for pyramids. There's surface area formula for cones as well. These are just not as common as these 3, so we're going to focus on rectangular solids, cubes, and cylinders. And again, like with the volumes, there's not much more I can show you how to use it. You just need to be able to identify your dimensions, height and radius for cylinders, height, length, width for rectangular solids or cubes, and then apply the correct formula. So if you have questions on specific problems about using these formulas, please schedule some office hours with me. If not, it's fairly straightforward. There's some word problems. There's some just calculating surface areas and volumes. But this is the end of 15.5, which means we have only one section left in the entire class.